Today we're going to find an all-important variable, the acceleration of the objects attached to an Atwood machine where the mass of the pulley is not negligible. Consider the system shown in the figure with MB greater than MA so that this thing can fall, where the mass and the radius of the pulley are M and R respectively, capital letters. Object MA is resting on the floor and object MB is a height h above the floor when it is released from rest. The pulley axis is frictionless. The cord is light, does not stretch, and does not slip on the pulley. Find an expression in terms of the given variables for the acceleration of MB, and then talk about how our answer would change if the pulley were massless. Let's get down to business and find the acceleration of mass B. But before we do that, let's talk about two important assumptions we get to make. The first, closer to being an actual fact than just to simplifying an assumption, is that the accelerations of MA and MB are equal in magnitude. Different in direction, because this one goes up and this one goes down, but they are connected. This is the same as it was in the easier version of this problem, where the pulley was considered to be massless. However, there is something different, and that's where our second important fact comes in before we begin. The tension in the rope is not constant throughout. If I talk about the tension holding this mass up, I should call it TB. And if I talk about the tension holding this mass up, I should call it TA. In the previous version of this problem with a massless pulley, we are allowed to say that the tensions are equal and use that as a shared variable in the two force equations in solving a two-variable system of equations. I get asked many times why this is the case, why the tensions must be different. And to answer that question simply, you just have to think about what's going on here. This pulley now has mass. It now takes effort to rotate this thing. I'm going to leave it at this. The difference in tensions in these ropes, and you know tension is like bidirectional, okay? I can say it goes this way, and that way, as well as upward, depending on your point of view. The difference in those tensions is exactly the effort that needs to be exerted in order to be able to rotate the pulley. If the pulley was massless, then no effort is required, and so we say the tensions are exactly the same. No difference in tension is required to bring about the clockwise motion you're going to see here. With that out of the way, let's go back to our old strategies of finding the accelerations of things, which of course involves free body diagrams and calculating the net force, taking advantage of Newton's second law to extract information about the acceleration. We draw a free body diagram on the mass of interest, and find that pulling us down, we have our familiar force of gravity, mg, or specifically mbg. Pulling us up is the tension in that string. We will name it TB, just like I said. We will realize that these are the only forces acting on our B mass, and so we will consider that altogether they make up the net force on mass B. The equation that diagram represents is this. The sum of the forces on mass B is equal to TB minus mbg. Here I have decided that the downward direction on this side of the pulley should be negative. That's why I have the minus sign in front of mbg. That's an important detail, and I'm going to have to be specific and consistent with that decision that I've made all throughout the problem. Now, we can say, being more specific with the net force using the definition by Newton's second law, that MB A is equal to TB minus MBG. Well, it's the end of the line, because although we're looking for A, and we don't need to know that, we do not have enough information to solve for it because we don't know TB. We don't know the tension over here. So as usual, I have to go to some other object in the problem and talk about the net forces on that. Let's see if mass A yields any answers for us. As usual, we consider downward force of gravity, MAG, and previously named our upward force of tension, TA. These must come together to make the net force on object A, and we write it out as such. Sigma FA is equal to MAG minus TA. TA is negative now. And so, Newton's second law, MAA is equal to MAG minus TA, and we're sunk again. We have no new answers. In fact, we've just made it worse, because although this also mentions A, it also mentions a new tension, TA, and that doesn't help us substitute into the red equation at all. That's where we go to the torque equation. Now let's talk about how at the end of the day we expect this thing to rotate in the negative direction as such, which is the clockwise direction, reminding you that the definition of torque is Fr sine theta, where F is the force on a point of the rotating object, such as these two, TB and TA. R is the radius from the center of rotation to the force, tangential or otherwise, and sine theta, theta being the angle between the radius vector and the force vector, in both cases here, 90. So we're going to ignore that and say that torque is equal to Fr for this problem. Now, the sum of all torques on our pulley is as follows. Left to itself, TB would cause us to rotate in the negative clockwise direction. So the torque for that, the torque expression, the force, negative TB, R sine of 90. So we leave it off. We have TA left to itself. That would cause us to rotate in the positive direction. So we have plus TAR similarly. Now the definition of torque, mirroring Newton's second law, where the net force is equal to MA. For torque, we have I alpha, moment of inertia times angular acceleration, is equal to negative TBR plus TAR. We can get even more specific, okay? Because the moment of inertia for a disc-shaped object, actually a cylinder, your rotational dynamics chapter in your book will tell you there's probably a page with a lot of shapes on them and what their moments of inertia are. For a disk is 1/2 mr squared. A lot of background knowledge required for this problem, right? And alpha has a simple definition as well. Alpha, angular acceleration, it so happens, is tangential acceleration over r. And the tangential acceleration of particles on the edge of this thing is coming from the rope, and it is the same. The rope is connected to the masses too, right? So each particle of the rope has the same acceleration. So thankfully, this A now is the same as the others we've mentioned. And that's equal to negative TBR plus TAR, which I kind of just feel like writing as TAR minus TBR, if you don't mind. All right, now let's do some algebra simplification. We have here a numerator of r squared, a denominator of r. That leaves one r to cancel in both, right? Now after having done that, we have r, r, r in each term on both sides of the equal sign. So all of those may cancel. We have here MA over 2 equals TA minus TB. And we could multiply everything by 2. You get MA equals 2TA minus 2TB. And check, check, check. All three of these equations mention A, TA or TB. And therefore we have 3 equations and 3 unknowns. What's left is the busy work of us trying to solve for A. And the way I'm going to do that is by getting the tensions alone in each of these red and blue expressions and substituting them into TA and TB here. So for this one, we have to add MBG to both sides. So we get MBA plus MBG is equal to TB. He's ready to roll. Here we can subtract MAG from both sides, get the following. And to get TA truly by itself, we divide by -1, which flips the direction of the difference here. Get MAG minus MAA instead of the opposite. And that one's ready to roll. And we're going to substitute TA there and TB there. Let's see what that looks like. MA equals 2. Now for TA comes MAG minus MAA minus 2. Now comes TB, MBA plus MBG, and close that. And we are very nearly there. We just got to isolate the acceleration. So the distributive property comes next. I'll not narrate everything, but just watch carefully. All right, so here we have that we're going to need to get all of the things with A on the left side of the equation with capital MA. That's going to involve adding 2 MAA and also 2 MBA to both sides of the equation. And that'll look like this. Okay, for the left side of the equation, we must factor out all of the A's, the greatest common factor, or actually just the common factor of acceleration, and that looks like this. And finally, we can divide both sides by everything on the left side that is not the acceleration, and your result looks like this. And there we have it. There is an expression for the acceleration. Just to point out some properties of this, I'm going to do one simplification. I'm going to factor out the 2g from the numerator here. So A will actually be equal to 2g MA minus MB over M plus 2MA plus 2MB. And the reason I'm showing you that is just to make it very clear about some of the properties of this thing, notably that this result should be negative. Think about it. We have MA minus MB showing up here. We've established that MB is greater than MA, so when you substitute whatever values belong in there, you're going to get a negative result. Okay, smaller minus bigger. That's okay. We were asked for an expression in terms of the given variables for the acceleration of MB, and we established that the downward direction on MB's side would be negative. If you wanted the acceleration for MA, then you just take the absolute value of this, and that A would also work for the tangential acceleration of the pulley as well. So that's the absolute value of the acceleration for any particle connected to this rope. in this problem, and that may be used to find a lot of interesting things that I've seen problems asked. Really, this is all the work involved in, for instance, finding the time it takes for this mass to reach the ground. Then it's just a kinematics problem where you know your acceleration and you know your distance. So I'll put some problems in the description that can help you explore that idea a little bit. So how would the answer change if the pulley were massless? If it took no effort to rotate it? That would mean there wouldn't have to be a difference between the tensions. That would mean that this TB and this TA would be equal. We might as well just call them T. The problem is much easier to solve because you have a two equation system to solve. The only unknowns are the tensions and the accelerations that are now shared by all the objects, and you don't need to write a third torque expression. Now, I have videos about that problem, but fortunately we don't have to do that whole problem. Because if the pulley was massless, guess what? We just get to take our result from before and zero out the mass, the capital M of the pulley. The magnitude of the acceleration then becomes 2g ma minus mb over, now with that capital M gone, we can actually do some simplification. You can take out the 2 of the denominator, so there's 2 ma plus mb. And awesomely, you now get to cancel out the 2's. So under these conditions, and again, the other earlier physics, about a month earlier when you're doing your undergraduate physics class, you'll find that the acceleration when the pulley is massless is actually equal to g ma minus mb over ma plus mb. Oh, and that's all in absolute values. So see if that isn't the case when you do that problem for yourself, and also look at my video on that topic, which I will add to the description when it's ready. Okay guys, good luck and thank you for watching. That was a long problem, so good job for sticking with it.